All right, let's go ahead and get started. So I'm going to do two things today. I'm going to finish talking about matrix multiply, which will actually take at least half the time, I think, and then make it more concrete. One of the comments or questions I got after lecture last time was it seemed pretty abstract, this whole idea of tiling and everything. So hopefully you'll have a much more concrete idea. I'm not going to give you exactly, the code that you will need to run, but try to give you some examples so that you have some pretty strong hints about how to get going on the homework 1 assignment. And homework 1 will come out later today. The partnerships will come out. Yeah, all of you hopefully are turning in your survey forms. If you haven't already done that, please do that immediately. And we will use those to set up, or Jenny and Marquita will use those to set up partnerships, and those will be announced on B courses by Friday. So hopefully, maybe even sooner, but probably by Friday. So be sure you filled out the survey. If you're not officially enrolled in the course, just assume that you're going to get enrolled in the course. Go ahead and fill out the survey, turn in homework 0, and then make sure that, and we will put you in a partnership. And we will try to, I think we'll start with some teams of maybe 3 if you've indicated that you're not quite sure whether you're going to take the course, just so that you have a better chance, make sure that the teams survive. Yes?
How would you, so if you're not in the course, you don't have access to B courses, so how would you like us to submit?
Oh, so you can either talk to Jenny, raise your hand, Jenny, just in case, okay, who's in the back of the room before you leave, or send email to the CS267_spring17@gmail.com. I should have put that. Send me email. I'll make sure I'll forward it to the group, and we're just adding people explicitly to manually to B courses if you're not yet officially enrolled. So. Yeah, good question. And we do really want a web page. I know people were asking, can I send you a PDF for homework 0? Can I send you a Word document? We just want to be able to link them all together so that people in the class can see what other people in the class are interested in. It gives you hopefully thinking about what you might want to work on for a final project and stuff. So that's the reason that just makes it easier. Yes.
I think it's confusing because the instructions at the bottom say submit a tarball, PDF, or whatever, but earlier on it says submit a website.
Oh.
So it's confusing. You're like,
which one do we want? Jenny, which one do we want? A tarball, or it says tarball PDF, or do we want a link to a website, don't we, for homework 0?
Anything like a file or a tarball.
You'll deal with the tarball or PDF? Okay, forget what I said. send whatever form you prefer, and Jenny will make sure it gets stuck on a web page so everybody can see it. Sorry, I didn't realize that we were going to go do a little bit of extra. I thought we just wanted the links to put them all together on a website, but anyway, so sorry about that, the little miscommunication. Okay, any other logistical questions before we get started? Okay, and the question, by the way, I didn't repeat it, but I think I said enough for the context was, if you're not in the class yet, not officially enrolled, send email either to me or to the course email list or the TAs, and we'll get you added to B courses. Okay, so I'm going to talk about optimizing matrix multiply, and then I'm going to give a very high-level overview of parallel machine architectures. And we kind of do this a little bit, I don't know what it's called, cyclically or iteratively or something. Well, I'll give sort of high-level overview so you have an idea of what parallel machines look like and how you think about programming them. Iden next week will be talking about different kinds of algorithms and how to go about thinking about parallelizing them. So it's useful to have a mental model of parallel machines. But at this point, we're not really telling you exactly how to write the code. And then we'll go back and say, okay, specifically, how do you do message passing? How do you write shared memory code? Things like that. So that's the idea for the next few lectures. And I will try to not pace quite so much, or at least not so far. Okay, so we'll do a little bit of a recap and then talk about some of these more specific things in terms of matrix multiply, and then go on to parallel machines. So this was our cartoon of what a machine looks like in general. This is just a serial machine, a single processor machine, and it's got the multiple levels of memory hierarchy, which have, on the order of magnitude difference in performance as you go down the various levels. And remember, we care about spatial locality, things nearby each other. If we can use things that are nearby, things that we have just recently used, then it's likely that those things will sit at a high level in the cache, because the way caches work is they don't load just one variable, one value, one byte, or one word. They load a bunch of them in. And so spatial locality is helpful for that reason. Temporal locality is if you can reuse exactly the same variable you've just used before, then that reuse is also going to be faster, because that thing will be saved in this faster level of cache, either on chip or in the off chip cache. Okay. Any high level questions? Okay, so here was our blocked or tiled matrix multiply algorithm, and this sort of pseudocode said, well, we'll read a block of C. So these are not individual elements. That's a little submatrix. And then we'll do a little matrix multiply. We'll read a block of A and a block of B. And we'll do a matrix multiply on these two little blocks here of A and B. And then add them onto the small block of C. And then write the result back out to memory. Okay, so that was that's your mental model of how the blocked algorithm works. It reads in these three blocks, multiplies two of them together, add to the third, and then write out the third. Okay. All right, well, the code doesn't actually look like that. And as I said, this is not code you can exactly take and compile, although it's pretty close. It's closer to it. It's a little mixture probably of C and Fortran here. But anyway, so it's because Jim is Fortran and I do C. So anyway, between the two of us, we sometimes have trouble with that. We debate a lot about row versus column major order too. But so what does the code really look like? Well, it looks like 6 nested loops instead of 3 nested loops, right? Each of the little red matrix multiplies of 3 nested loops. We know how to write matrix multiply, and so we nest that in the code that is running over all of the blocks. And so the three outermost loops are jumping by B, so they're jumping by a block size, and then the innermost 3 loops are actually just doing the little matrix multiplies locally. Okay. So that's what the code looks like. Now the other thing that's missing from this code, what happened to our read the things out of slow memory and write the things back out to slow memory? Well, the hardware is doing that for us. Okay, so what we're trying to do is to just by accessing in the right order, we're hoping that the hardware will move these 3 blocks into fast memory. They won't all happen at once. They'll kind of, as you start to access variables inside this inner loop, it'll start to read things into cache. But because we have a lot of temporal locality in this algorithm, and we're going to reuse the values of A and B. And if we make them small enough, they'll all fit in the cache. And if our cache is kind of well architected and so on, we don't have a bad behavior, those 3 will sit in the cache after the first time each of those values have been used, and they will sit there, and we'll get to reuse them all of the other times after the first time. Okay, so we're not really writing code that manually moves them into and out of memory. There are some machines that we'll talk about, including Cori, the machine that does have some memory we might want to do that for. But when we're talking about caches, the hardware is doing that for us automatically. Okay, any questions? Does that make the idea of tiling more concrete, or is it still a little? Do you have any questions to make it more concrete? Yes.
So in practice, you just have to kind of tweak the parameters of the block size to figure it out.
Right. So the question was, in practice, do you have to tweak the parameters of the block size? And that's exactly right. In fact, that is my next slide. So what happens? We have to figure out how big to make the tile sizes, right? Because if we make them too big, they won't fit in the cache. And which cache are we talking about? Are we talking, if we've got a machine with 3 levels of cache, are we talking about the L1 cache, the L2 cache, or the L3 cache? And if we make them too small, we don't have as much reuse. So we want them to be as big as possible, but not too big. Okay, that's the general rule of thumb. And this is looking at tiling for the cache. And the problem is we can also tile for the registers, and I will say a little bit more about that a little bit later in lecture. But in this case, we're just looking at some data that this group collected on tiling for the cache. And you also need to worry a little bit. Remember, I told you last time that the cache, what it's doing is it's storing a memory location from the DRAM, from the slow memory, and it kind of puts that in the cache and it says this is from this address in memory, and here's the value that was sitting at that address in memory. So it keeps track of where it came from and where it needs to go when it writes it back out again. But it can also have, you can have problems because there can be multiple places in memory that all map to the same thing. So if you have what's called a direct map cache, meaning that you can only put one thing that kind of comes from that address at each one of the locations in memory, and you have a really bad matrix size, then it could be just coincidentally bad that you can't fit more than one block in the cache at once, because A sub 0, 0 and B sub 0, 0 and C sub 0, 0 all end up in the same place in the cache, and they knock each other out. So that's called interference, and it's a bad thing. And for that reason, the caches are going to have some level of associativity, and that means we can store a few things in that place in the cache. So the cache will be bigger, so we can store a few things just to prevent certain kinds of really bad behavior. But this is looking at a real machine, and it's looking at, I meant to put the problem size on here. I think this is we're looking at these different tile sizes for a I think this is over like a 1K by 1K matrix, and these are what normalized metrics. So what they did was they took the lowest and the highest value for everything they measured for all the different parameters, and then they looked at what percentage you're getting relative to the best case. So you can see up here is the best case for a number of the different metrics. So what are the metrics they're looking at? Well, the first one is the L1 cache misses. That is how many times that you go and try to read or write something and you're hoping that it's in the level 1 cache, because that's the fastest level of the memory hierarchy we're talking about, and it's not there. So you have to go off, and that's called a miss. And so we're counting the number of misses. So we want these things to be low, right? So the green line is how many cache misses do you have? And for each one of these different sizes, then we're getting different different cache misses, and the L1 cache misses are look pretty low. Then we've got the L2 cache misses, and those are they're generally pretty low also, but then you get a size here when it gets to be too large where it falls out of the L2, then the execution time follows sort of a similar pattern. That's the lighter blue line here. So what are the other two times? The other two times, and this is really the main point of this study, is to say, what if I just made the tile sizes one larger than this? And if I happen to have picked, these are pretty good tile sizes that I had before, and if I just make them a little bit larger, so for a B+1 size block, we're going to get performance that is very different. That's much worse. And so in that case, you're getting misbehavior and as well as running time that can be a lot worse for these different parameters. So the point of this is that you really have to be careful about exactly how you pick these tile sizes. Okay, so in practice, tuning the code can be really tedious. And by the way, I think I forgot to mention this, it was on the slide, that we don't always make these blocks square. They're often not going to be square. Why would you not want them to be square? Well, remember that your arrays are either laid out by rows or by columns, and one of those, whichever dimension is the kind of good dimension, is going to be much faster to read from than the other dimension, and for that reason you may want the block size to be rectangular. And oftentimes you can't fit square blocks. You can make a larger block size if you make them rectangular, because you can't fit 3 square size matrices in that all fit into the cache. So it becomes a very large parameter search to figure out what is the right block size. So there's lots of variations. I actually was looking at all the different papers on tile size selection. In fact, it became such a popular area of research, it was just called TSS, for tile size selection, and about 10 years ago there were lots and lots of people writing papers on how to predict the tile size. And what they would do is they would try to look at, for example, the cache size, what level of associativity had, and things like that, and come up with a formula that would predict what is the best tile size. So we did something else around the same time, which is we were looking at this and said, well, this is really annoying. And in fact, the models, if you actually try to get a good model that predicts exactly what the right tile size is, it becomes very complicated. And so it becomes so complicated that we decided it was easier to let the computer search for the tile size than for us to try to figure out what the tile size should be. It's also the case that, as I mentioned last time, a lot of the hardware specs are not that easy to find. So exactly what is the level of associativity and things like that. Maybe you've got some code that's written for one platform, you try to move it over, and suddenly you got to go look at the hardware manuals to figure out what the cache sizes are. So we developed the idea of automatic performance tuning here at Berkeley, and a couple of other groups were working on this idea as well for other algorithms. And I mentioned this last time, but there was a project called FEPAC that was kind of inspired by a CS267 homework assignment based on homework 1. It turned out, though, that FEPAC was actually, although the students had taken this class and were inspired by it, they were actually trying to optimize deep learning neural net algorithms. Okay, so something very popular today. And at the time, people said, oh, these things are never going to work. They were doing speech processing. But anyway, they weren't saying they weren't going to work. But it wasn't very clear at that point in time that they would. And of course, now it's very popular. So that's where the auto-tuning idea, specifically for matrix multiply, actually came from. There are other people who have developed this idea of searching, letting the computer search for the block size and things like that for other algorithms that we'll see later. We'll look at there's a group called Spiral that does this for FFTs, for example. There's also a project called FFTW, the fastest Fourier transform in the West. And for some algorithms, you can do this offline. So for matrix multiply, it turns out that the only thing that matters, it doesn't matter what data is in the matrix. Multiplying a 0 times something else is not actually any faster than multiplying a big, huge number. And so the only thing that matters are the dimensions of the matrix. But the dimensions of the matrix actually matter a lot. So you can have square matrices and tall, skinny matrices and short, wide matrices, and all these different things will affect your tiling strategy and therefore affect how you optimize for it. So I still think it's useful for you to understand how to do it by hand. I'll talk later about the fact that there's been a lot of work put into highly optimized libraries. So in general, for most of you, you're not going to have to optimize matrix multiply except for this homework assignment. Okay. So this idea of searching over the block sizes comes up for high-level algorithms. I guess there's one other reference here. I've really said most of this. So there was was an interesting paper a number of years ago by Sid Chatterjee and others where they tried to develop a really, really accurate performance model, mathematical formulas that told you exactly how the architecture of and I believe it was an IBM system, how it was going to work and what the performance was going to be. So you could predict what was the performance of this algorithm by looking at this set of formulas. And it turns out that it was many pages of formulas to get figured out because you had 3 levels of caches and things happened in the DRAM. You had virtual memory system and registers and all this kind of stuff. So that was a little bit of a disappointment. Now, I should say that the paper that I showed the other data from is actually a more recent one, and they do have an analytic model that they think is useful in practice, and whether it gets exactly up to peak or not, you can go and look at that if you want to see it. But there are still people who are working on this. But as I said, it was a really popular area for a while. Okay, so what does the search space look like if we're looking for that? Well, you already saw a little bit of the search space in that previous graph that had these kind of all these lines that said, well, if you just make the block size off by 1, you fall off a cliff. This is actually looking at, in some sense, a much simpler problem, which is register blocking. So what if I just want to figure out how big the registers should be, the register block should be? So typically, how big would a register block be? It might be something like 3 by 3, 2 by 2, 2 by 4, something like that, because all you're trying to do is to load 3 little tiny matrices into the registers, right? The set of registers that you have that are sitting there right there next to the processor that's going to do the arithmetic, and then do a little tiny 3 by 3 matrix multiplier, whatever it is. And what this is called, this is a color heat plot, and this is the number of rows in the register block, and this is the number of columns in the register block, and what the color is telling you is how fast is it going. So there's one really great data point here, which is let's see, what is that? I believe that is 2 by 4 data point. And so that is the 2, 4, 6. I think that is actually 2 by 3, isn't it? Probably. The 2 by 3, what's that? 3 by 3? I don't think so. Well, I know these things look a little bit off, but no, I think it's 1 over from here and 2 up from there. So I think it's 2 by 3. But the main point is that if you're off by 1, you can get a really, really slow performance, right? So that red point, that dark red point, is the best performance over here, and this is the scale that we can see, and all this other stuff is really bad performance. But these are the places where there was actually where we were looking at all the data, and so there's some other points that aren't too bad here. 1 by 6 isn't too bad. But in general, you really want to get that size right, because if you get the wrong size, it's going to really be a problem. And typically, for if you pick register block sizes, and especially cache block sizes that are a little bit too small, it's not a big problem. If you pick them a little bit too big, it can be a really big problem. A little bit too small can surprisingly be a problem if it changes what things interfere with each other in the cache or something like that. But that's why it's so hard to do. So. So the group here built this package called FEPAC, the Portable High Performance Computation package, and Then a group at University of Texas, led by Jack Dungara, built another version called Atlas, using the same ideas. And then this Atlas package has become quite popular, is still maintained today and run today on a lot of different platforms, and is actually used by default inside of libraries and inside of packages like MATLAB. So Atlas has really been widely adopted. Because it takes a long time to figure out how to optimize these codes by hand. And so it helps that matrix multiply, dense matrix multiply, first of all, really benefits from doing the optimizations well. And secondly, that it doesn't depend on the values. It only depends on the matrix dimensions. And so you can optimize for a bunch of different things. This is, I believe, a fairly large, there's n is equal to 500. And here we're looking at the Atlas is the blue line, the vendor optimized BLAs. And by the way, Intel, for example, has a group, I believe they have been in Russia. They're about to move, I think, to Seattle area or maybe Portland area. But anyway, there's a group of people just focused on making these numerical libraries run fast, including matrix multiply. And so you can see that Atlas does pretty well in many cases as well, or even a little bit better than the vendor hand optimized BLAs, even though in the hand optimized BLAs, you have people who are sitting right next to, hopefully, or at least talking to the hardware designers. And on the other hand, if you use the BLAs, I will just define that term later, but we're referring to the matrix multiply operation. Yes?
On the previous slide, why isn't it symmetric, 3 by 2 versus 2 by 3?
Because of this column versus row major layout, something about loading things in a column, it can be, like if it's row major layout, it can be slower to load a big column of things into the register. So, and exactly how that turns out in practice, to be better or worse in one way or the other is not always obvious, but that's a good question. That's the reason that, sorry, I didn't repeat it, the reason that the performance is not symmetric. But 2 by 3 can be different than 3 by 2, for example.
Does it depend on the language you use?
Oh, good question. Yes, it absolutely does depend. The question is, does it depend on the programming language that you're using? It absolutely does depend on the programming language because the matrix layouts are very different. So if you're working in a language like Fortran, where it's column major, versus a language like C, where it's row major, then you'll get different behavior. If you're working in a language like Python, where I think for a matrix, the default would be an array of arrays. Is that right? But anyway, for languages in which you don't actually have a contiguous chunk of memory, what you have is an array, and each one of the rows, for example, is a different array. That would be really different and much slower because you can't just index to find all the elements. Yes.
So does this speed also depend on the actual computer you're using, like running on my laptop versus your laptop? Because different computers might have different chips and architecture.
Absolutely. So I think that even if you have, so first of all, it depends on the architecture, that is the instruction set architecture. So running on the Cori Phase 2 system, which has a nice landing processor in it, is going to be different than running on a IBM power architecture, something like that. But even within an architecture, if you have a somewhat different memory system, so you have a different kinds of DRAM or something like that, it may kind of look like the same architecture, but it can have different performance.
But then what's the point of any optimization? Because if you optimize it for your own computer or whatever computer you're optimizing it for, then you can hardly use it for any other.
Yeah, so the question is, what's the point of doing this if every time you come to a new computer you have to redo the optimization? And that is actually the point of having the computer do the optimization rather than you doing the optimization. So we think of this as happening at what we call install time. So somebody is installing a linear algebra library, and at that point they spend, hopefully it's built into something like Atlas where it would do this, and it'll say, go off and run all of the tuning stuff, try all these different block sizes and things like that, and pick the best parameter for this machine. And so, yeah, it does depend on the exact characteristics of the machine. In some cases, the code will port over pretty well across similar machines, but yes.
Do supercomputers like Cori use the same virtual memory abstractions that personal computers would use? Because it seems like that could affect your results a lot.
Yeah, so the question is whether supercomputers use virtual memory abstractions like supercomputers do. There's a couple of answers to that question, and I guess the simplest one is yes, they do run an operating system that has a virtual memory notion, so that it has pages that can be mapped, and you'll have a TLB, which is a piece of hardware, and that will show up. This other level of the memory hierarchy will show up even on the supercomputers. What you don't typically do in a supercomputer, and this is one of the big differences between a supercomputer and a cloud, is there's no local disks attached. So the virtual memory system, although it's got those mechanisms in it for allowing you to kind of have a large namespace of addresses, it will not, and for those of you not familiar with the term virtual memory, it allows us to have a whole bunch of addresses even if I don't have exactly that much physical memory, and then the hardware system will figure out how to map those onto the physical memory that we have. And it's really popular if you're running on a workstation. Those can be living, the actual memory locations can be living on the disk, and just like a cache, then it'll be the operating system will move the data in and out from the disk to the DRAM. You can see really, really awful performance. In fact, there was a graph that was in my lecture from last time that I didn't talk about, but that has this graph where matrix multiply gets really, really slow because you're going out to virtual memory. So supercomputers don't have the disks attached to the nodes. They'll have a separate storage system. The operating systems on the supercomputers also tend to be, in some cases, a little bit different. They tend to be a little bit simpler because the other thing you'll have, and I actually was running just one of the simpler benchmarks on my laptop this morning and thinking, oh, I'll show you one of those plots like those memory benchmark plots for my laptop, and it looks like this because there's all these other processes running on my laptop. So a supercomputer will be a much quieter sort of environment. You'll have some things that are running, but not nearly as much. So, okay, good questions. Okay. All right, so main point of this is, you need to optimize this stuff. You do not want to run at the Fortran 77 kind of standard implementation. That was just a vanilla implementation of dense matrix multiply. You want to run something that's highly optimized for caches and so on, but the autotuner does about as well as the hand optimized code. Okay, so what I've mostly talked about in tiling, I showed you these 6 nested loops that come from the tiled version of the code. We kind of talked about the fact that you would also have register blocked code. So that was kind of cache blocked code. You could have register blocked code, which could look the same, although it turns out when you register block something, you might want to write the inner loop a little bit differently because it's such a small matrix multiply. But what if you want to optimize for, say, 3 levels of the memory hierarchy or 2 levels? So we started, if we had 1 level of memory hierarchy, cache and DRAM, we turned our 3 nested loops, or sorry, if we just had 1 level, we had 3 nested loops. If we have 2 levels of the memory hierarchy, we ended up with 6 nested loops. If we had 3 levels, we have 9 nested loops. You can see this code, although it starts as 3 simple nested loops, starts to get pretty complicated, or at least pretty large. And it's not always obvious how the different levels interfere with one another and which ones matter. And so that's one of the things you'll be looking at in homework 1 is which of these kind of levels of optimization actually make a difference. But because of this problem that you have all these different levels, people developed the idea of what are called cache oblivious algorithms. I believe this was from Charles Laserson and his group at MIT first came up with some of these cache oblivious algorithms. And here what we're going to do is we're going to think of the matrix multiply as a, we're going to have an n-by-n matrix multiply, and we're going to think of it as a bunch of smaller problems, which we were in some sense already doing when we were tiling it, but we're going to just break it down into a fixed number and do that recursively. So let me make this a little more concrete. So let's think of our matrix. So it could be a big set of matrices. For simplicity, we're going to make each one of these square matrices, and we're going to assume that the matrix dimensions are a power of 2, just so I don't have to write a bunch of ugly code to deal with the corner cases. But you can extend it to those other corner cases. So I'm going to take each matrix, and I'm going to think of it as being 4 submatrices, which I'm just writing with a notation C11, C12, and so on. Fortran indexing here. Then what I'm going to do is say I can write my matrix multiply of C by just multiplying these submatrices. So the dots in that line up there are really referring to matrix multiplies of what could be pretty large submatrices, right? That's a quarter of the matrix. And so Here's a little bit of pseudocode once again for our RMM, which stands for recursive matrix multiply. And it says that in order to get back C from inputs A and B of some size n, what I'm going to do is call matrix multiply on A11, B11, and that's half the size, multiply my A12, B21, sorry, 1, 2, and 2, 1 together, and so on. So you get all of the 8 matrix multiplies from the combinations of things that need to be multiplied together. Okay, so that's just a simple recursive algorithm, and it turns out that this is going to perform pretty well in memory. So why is that? Well, we'll do a little bit of theoretical analysis here and try to figure out, first of all, what's the computational cost of running this recursive algorithm, and then what is the data movement cost of running this algorithm. So once again, we'll just be thinking about, in our heads, we might be thinking about a single level of the memory hierarchy. So imagine that we have some amount of memory, we'll call it M fast, that is our fast memory, and everything else. The matrices start out in slow memory, and they can move into the fast memory. So how many arithmetic operations are we doing? Well, in this recursive thing, we're doing 8 times the number of arithmetic operations we have to do on a problem size that's of half the dimension, so A of n over 2. And then we have 4 add operations that we have to do. Those are the 4 pluses that you see in the recursive call inside of the code there. So you have to add those results together. And what is the size of those add operations? They're the size of a matrix that's half the dimension, but it's a square matrix. So the number of adds you actually have to do is 4 times n over 2 squared. And that's true if n is greater than 1, and otherwise you just have 1 multiply you have to do. Okay. And I won't go through the math here, but you get a geometric series that simplifies into 2n cubed, and that is the same that we had before when we had our 3 nested loops, where it's a little bit easier to count things. Okay? Okay, well, so that just kind of confirms that, all right, this is doing the same amount of arithmetic that we were doing before, and now the question is, well, what happens in terms of the data movement? Well, let's see if we've got how many words we're moving between our slow and fast memory in the recursive algorithm. Well, we'll kind of assume that we've got to start by moving the 8 things in to our fast memory. So we have 8 times whatever the data movement cost is of our 8 subproblems, each of size n over 2. And then we have to do the adds. Well, how much do the adds cost in terms of data movement? Well, again, we'll assume that if the matrices are too big to fit in my fast memory, what I have to do is I have to load each of those 3 matrices in. So that's 3 times n over 2 squared, the size of those matrices, times the 4 adds that we had to do, because we have to load them in each time for each one of those adds. And that's true if 3n squared is greater than the fast memory size, than m fast. Okay, so that's true if we can't fit all 3 matrices in. This is a simplified model. This is not worrying about exactly what is in the cache or what is not in the cache. Think of it now as a kind of an explicitly managed memory hierarchy where we load in exactly what we want. And so in this case, we have to be able to fit all 3, just fit all 3 blocks in. So we're assuming we can exactly fit those 3 blocks in if they have the right size. And otherwise, it is just going to be the 3n squared that it takes in order to just load the 3 blocks in. Okay, so this looks, I mean, they may be even worse than the arithmetic one, but the point is that the recursion cuts off much sooner, right? Because once you get to the point where you have 3 matrices that fit in your fast memory, at that point you pay once to load those 3 matrices into your fast memory. That's the 3n squared over here. And at that point you're done, and after that there's no more slow memory traffic as you work on smaller and smaller problems. And so this is what we get is the order of memory operations is n cubed over m, the fast memory size, the square root of the fast memory size, plus n squared. So this is the same as what we had last time when we talked about the optimization of block matrix multiply. That is, we get to this order n cubed over m, the square root of m, the fast memory size. Okay, so this algorithm also gives you that kind of performance. And the important thing is we used mfast in this analysis to show that we were speeding it up, but we don't have to write the code, right? There's no mfast up here in this code. Whereas before we had this b and we had to figure out what is b, and this says, no, don't worry about what b is, just write it recursively, and eventually the 3 matrices will fit in cache and all will be happy after that. And so it could work for 1 level of memory hierarchy or 2 or 3 or whatever. Okay? So that's the theory. Remember the difference between theory and practice, though. In theory and practice, you typically do cut off the recursion at some point. What does that mean? Well, because every time you call RMM, that recursive function call, there's a little bit of overhead that may not seem that high, but when you get down to the point where you're multiplying little tiny matrices, a function call can be pretty substantial overhead. And so what you actually typically do is you kind of cut the recursion off at a certain point, and then you have a highly optimized code that's not recursive down at the bottom. And you say, wait, but now that was the whole point of trying to avoid picking a block size, but picking the point where you have to switch over to microkernel, as long as you don't make it accidentally too big, you make it small enough that you're amortizing the cost of your function call overhead, it is pretty much portable across machines. It's not something you have to really tune very carefully. Just don't make it really big, because then it won't fit. And then it turns out that also you do have to very carefully implement the code inside of that little microkernel. That is the point at which you've decided to stop the recursion. And in this one study done by Keshav Pengali and others, they reported they could never get above 2/3 of peak, whereas we're hoping that you're going to get closer to 90% of peak if you're doing matrix multiply on a processor. And if not, you should understand why you're not able to get more than that. And actually, Cori will be, phase 2 at least, will be an interesting exercise in that case. So the other issues that come up here is a lot of times, but just because of other details of the hardware, these recursive microkernels are not going to run quite as fast as just using loops. And you have to make sure you're worried about, remember I said there's a little bit of parallelism in the memory system where you can actually issue a load where you're saying, I think I'm going to need this value, and it turns out you need to put this kind of stuff in the code. So it doesn't really completely eliminate the need to figure out how to write that microkernel. Yes?
So it seems that if you're going to cut stuff off, then the cutoff size would have to be bigger than like the amount of stuff that could fit in your fast memory. Is that true? Otherwise, the cutoff won't do anything.
So I think it's the opposite of that. The question is, how does the cutoff size have to be bigger than the size that fits into fast memory? And the answer is no. What you want is the recursion to automatically get you to the point where you've got 3 problem sizes that do fit into your cache. They may be a little bit smaller than what you can maximally fit in your cache. So you may not be, that's why you might not be all the way up to the maximum point that you could run, because you won't have quite as much reuse as if you made them larger. But you want to cut it off, because at the point you're cut it off, you're not going to do any tiling or stuff like that inside the microkernel. You're just going to run, sorry, that's the key point. Yeah, you're just going to write code. You still have to worry about these weird things like prefetching and stuff, but you don't have to worry about blocking inside the microkernel, except maybe for registers. Okay. Okay, good. Any other questions? So there is some more recent work that's been done at Berkeley, and this is more for the parallel case. So I think you'll hear about that later when we talk about linear algebra, and it's kind of in between the fully cache oblivious algorithm and the fully cache aware algorithm, which is what we call the one that has an explicit B inside of there for the tile size. Now, one of the problems that I mentioned is that the data layout may not be so great. Remember, we had this picture last time of, one row of the matrix maybe sitting on all these different cache lines, so just depending on exactly how things are laid out, if you try to load a block, that code, remember, that I wrote before, the tiled code, going back to this one, even doesn't do anything about the memory. The memory is what the memory is. So these matrices are stored by column or by row, whatever they're stored as. In homework, I believe you're going to be looking at storage by column format. And so just exactly how those columns lay out in memory, this is each total matrix is going to be one contiguous chunk of memory. But exactly what happens to the caches and things like that will depend on what the sizes of those columns are, for example, and how things wrap around. So going across a row can be really bad. So if you really want to run a blocked algorithm, you might say, well, maybe I should use a different matrix layout. Maybe I should use something that is blocked. And people actually do that. They use blocked layouts for their matrices. But you say, well, I'm kind of thinking of this recursive algorithm. What would it mean to have a blocked, a recursive layout so that at every block size, I would have a contiguous chunk of memory? And so what comes up are these cursive layouts. And what I'm showing here is an example of a Z-Morton ordering. And that's because it looks like a Z. So what does this mean? So I think of my matrix also as being recursively laid out in memory now. And so the elements in order are this one, this one, this one, and then that one, okay? And so that means that that may be a huge matrix, right? But if I'm writing a recursive algorithm and I pick up the upper left block, well, that'll be relatively close to each other with nothing else from the rest of the matrix mixed into it. And then eventually I'll pick up a submatrix of that, and that'll also be a contiguous chunk of memory and so on. And that's true throughout the matrix whenever I pick up one of these blocks, as long as they're aligned with that recursive decomposition, then I'll get something that's nearby each other in memory, so I'll get better spatial locality than I do if I use a row major or column major layout. And there is an optimization that comes up in some of the algorithm and some of the libraries and things like that, and you can certainly explore this in your homework, which is doing a copy. It's called a copy optimization. That's where we're going to force you to read in the matrices in our column major layout just so everybody is playing the same game. But you may want to copy your matrix into a different kind of format and see if you can get it to go faster. Okay. So what happens in practice with all these optimizations? Well, first of all, tiling for registers, although I showed that tiling code as if it were 6 nested loops, and so the inner 3 loops are doing a little matrix multiply, and if that's a register blocking, that may be a loop that goes from I to I plus 2, and then from j to j plus 3 or whatever, if it's 2 by 3 loop nest. So those would be pretty, there's overhead of each of those loops as well, and that can be expensive. And so what you often will do is unroll that innermost loop, the register blocked loop, so you just have the 6 multiplies that you need to do, or the whatever number of multiplies that you need, 9 multiplies or whatever you need to do in order to multiply matrices of that size. So you can just kind of write the straight line code that only works for a 2 by 2 matrix, 2 by 2 matrices or something like that. You can also try to tile for multiple levels of the cache. You can, that we already talked about, or the virtual memory system. You can try to find some fine-grained parallelism, and I'll say a little bit more about these other techniques in a minute. And you should know that that the compiler, and being a compiler researcher myself, I know this the hard way. We tried for many years to automate all this stuff. We were trying to make it so that you would not have to worry about all this stuff. And the problem is now that if you're a performance programmer, which all of you are going to be in this class, that the problem is you're now trying to kind of reverse engineer what the compiler is going to do for you and what you need to do automatically. And one example actually from this class a few years ago was people were trying to do some loop unrolling, and what they found is that if they unrolled the loop once, they just kind of had 2 copies of the loop body, then the compiler would automatically unroll it 3 more times or whatever. And if they didn't unroll it at all, the compiler wouldn't unroll it at all. So they couldn't make it exactly 2, which is what they wanted, because the compiler was outsmarting them. So anyway, you've got all these flags on the compilers that you'll have to also play with, and you can try to do things by hand as well. So here's some other references to things you can look at for inspiration, and also, as I said, things like the Atlas library, which are very widely used in practice. So what are some of these other things that you may want to look at in general for matrix multiplier for other algorithms? One of them is removing false dependencies in the code. So in this particular code, where we've got this. We've got just these 2 statements here. So what's the problem? Well, one of the things that compilers have to do in order to figure out that they're going to do any kind of optimization in your code at all, or almost any optimization, is they need to understand what statements are dependent on what other statements. So when are 2 variables actually going to read and write to the same location? Because if I change the order of 2 writes, or I change the order of a read and a write, it'll change the behavior of your program. And generally the first rule of compilers is don't change the behavior of the program, don't get the wrong answer. And so they try to do that. Well, the problem is, especially if you're writing this in a language like C, it looks at that statement, those 2 statements, and says, is A sub I plus 1 the same as B sub I? I don't really know. So can I reorder these things or not? And so you can write things out in such a way that you make it clear that because these are just simple scalar variables, then the compiler can tell that they're not the same variable.
Between AI plus 1 and BI, why would it confuse those?
Let's see, AI plus 1. Well, or between AI and BI plus 1, either one. I think that's the note here is actually about the opposite order, but either one of them is a problem. So it's either a read after write or a write after read. So the problem is that what are A and B? A and B are actually just pointers to memory, and it doesn't know if they're pointing right next at the same thing or pointing, you know, one off at the same thing. And so it's possible that AI and BI plus 1 are actually the same location in memory, or that BI and AI plus 1 are the same location in memory. So, and different languages have different rules about this kind of stuff. So Fortran is a language in which one of the things you can do to kind of get the compiler to understand that A and B are completely unrelated arrays, they're unaliased, they don't alias to the same memory location, is you can pass them into a function. Because the rule in Fortran says if I've got two arguments coming into a function, I can assume that the compiler can assume that they are not alias. So you're not allowed to pass two arrays into a Fortran function that actually overlap in memory. Okay? However, I was talking to a compiler writer at a compiler company a few years ago, and he said, well, the problem is that not all the Fortran programmers understand that rule. And so people do write things where they, for example, pass into a function f of a, and then inside it, it looks like it's f of x and y, and it tries to reorder things in x and reorder things, you know, with things in y. But actually, they're both the same array, and so then then the compiler gets the wrong answer relative to what the programmer wrote. So, so they actually are backing off this assumption in Fortran. There's other things that you can do in C, like you can put the restrict keyword on pointers. You can use various compiler flags or pragmas or things like that to try to coax the compiler into understanding that A and B are really different arrays and don't overlap at all. Okay? I know you're really excited about this now. Okay, let's say that we want to, we have a slightly different algorithm. Let's just make this simpler. We're going to apply a convolution, and this is just looking at a little filter. And what we want to do is make sure that certain values go into registers, so they get into the fastest possible memory on the computer, as opposed to sitting even in the level 1 cache. And so this convolution, what it's doing is it's taking a little 3-element array that has filters 0, 1, and 2 places. That's the little blue array there. And it's going to sweep through another big array. Imagine that's a big array that doesn't fit all in your cache. You're going to sweep through that and apply the filter. And what you'd like to do is to encourage the compiler to put the 3 values that are in the filter array into registers. But it might not do that automatically. And so you can rewrite the code like this to say, well, let me just make a scalar variable, a simple float variable, f1, f2, and f0, f1, and f2 in order to encourage it to put them into registers. And then it's going to reuse those 3 values as it sweeps across the array, so that'll probably make it much faster. Okay, and by the way, there's also a keyword called register that you can add in some languages. For them, I would say in general, C compiler writers, I should say, believe that they are smarter than the programmers, so it's not clear they always pay attention to the register keyword, but you can try. Loop unrolling, I talked about that before, but maybe it wasn't clear what I meant by it. So what we can do is to unroll, this is the same convolution loop, and so rather than looping through that little filter array, I can just write out the 3 statements that are doing each one of those operations. And that can be a good thing. So that avoids some of the overhead of saying, am I done with the loop? Am I done with the loop? And so on. Because that can really slow your program down. It can cause other problems. Anybody have an idea of what some of the problems are with loop unrolling? Yes?
You might get to the end of the loop, and if you unroll 3 times and you don't exactly have a multiple of 3 number of iterations, you're going to have to add some other checks in there to make sure you accidentally don't go too many and overrun the bounds of your array.
That's right. You've got to have some cleanup code to deal with the fact that some of it doesn't fit into whatever your unrolling dimension is. Yes?
You can thrash your instruction cache.
Right. So the other problem is that if you make you've got another cache, or think of it at least as a separate cache for your instructions. That's all of the assembly language instructions, and it's loading those into a cache and hopefully reusing them. So what you just did is you made the code actually bigger, not just the code we see on the screen, but the compiled assembly language code. And so that can cause you to blow out your instruction cache, and actually, basically, it's code bloat, which will make it much slower. Was there another question? Yes.
It's hard to read, which adds programmer overhead time and makes mistakes more likely.
Oh, yes, well, right. So the other comment was some of these things that you're doing are going to add programmer overhead in terms of the amount of time to write the program and to make sure the program is actually working correctly. So certainly the version, well, in this case, maybe it's not so obvious whether this version or the version that had a little loop that went from 0 up to 2 was an easier version of the code to debug. But in many cases, when you unroll it, the code will get much uglier and much harder to debug. So it's a very good point. Another reason why hopefully people will automate this for us. You may want to, I talked before about the fact there's these pipelines in the processor architecture. So you may want to worry about exactly what instruction mix, what kind of operations can be done in parallel. This is a little bit different than vectorization or even a fuse multiply add. This is where you've got an add unit and a multiply unit, and even if they're working on completely different variables, maybe they can be done in parallel. So you might want to write code that has the right kind of instruction mix. Obviously, you've got a limit in terms of you've got something some problem you're trying to solve, but you may be able to write things in such a way that you get a better instruction mix for that algorithm. This is the copy optimization I mentioned earlier. In this case, we might want to just reorganize our matrix from, say, column major layout into block column major layout, where each column contains little 2x2 blocks. So that would be another example. Okay, so those are kind of all the tricks for how to really think about, that at least that I'm going to tell you about for how to worry about making your code actually run faster. Yes?
For this copy optimization, there's like a pre-processing step that you do on the data in memory to reorganize it?
Right, so the question is this a pre-processing step that you do on the data in memory? And that's absolutely right. So you do this at runtime. So you get, so let's say that you're writing the implementation of the matmul routine. And the first thing you do in the matmul routine is you say, give me, take matrix A and copy it into another matrix A prime, and B and copy it into B prime, and C and copy it into C prime. Not necessarily a good thing to do, right? Lots of memory overhead you just added. But remember, for matrix multiply, that's an order n cubed operation, and that involves memory traffic as well as floating point operations. And so sometimes the copy operation pays off, and sometimes it'll be a terrible thing to do. And generally speaking, it's going to work a lot better if it's a larger matrix. So even though you're doing a big copy with a larger matrix, you've got a lot more compute time inside there in order to do that. So then you end up with branches in your code that say if the matrix is bigger than such and such, they do the copy optimization, and that slows the code down too, right? So there's lots of things to worry about. Yeah. Okay, so any other questions about kind of the pragmatics of some of the things to try? And we will remember, one of the reasons to fill out the survey, hopefully you all filled it out and you did it really carefully, is to try to pair up people who know a lot about computer architecture and compilers with people who know a lot about what you want to do with matrix multiplies. Okay, I will tell you just a little bit about another matrix multiply algorithm, and this is kind of so that you're well educated on the idea of matrix multiply and you understand what people do. For a couple of reasons, people don't use this algorithm all that much in practice, but the traditional algorithm, as we've talked about, whether it was tiling, cache oblivious, or whatever, was an order n cubed flops algorithm. It turns out that there is an algorithm that has asymptotically lower flops. There's actually a few of them, several of them. And the original one is by Strawson, and it has n to the 2.81 flops per. So that's the order of magnitude. So what does this algorithm look like? Well, fortunately, because we already talked about the cache oblivious algorithm or the recursive algorithm, you've kind of seen the basic idea behind this, which is I'm going to think of my matrix as being, we'll just think about square matrices, and we'll think about power of 2 matrices, dimensions. And so we've got our little matrices that are going to be divided into these 4 blocks. But rather than doing kind of the obvious things of multiplying those subblocks together in the obvious way, I'm going to compute these other formulas. And they may not be so obvious why you want to do this, but here's one that's, subtract A22 from A12, and then multiply that times the sum of B21 and B22. Why? Well, because somebody looked at this really hard, and they realized that if you did this, you can actually do it in fewer floating point operations than the original kind of the naive code does. So these are the 7 statements that you have. There's 7 multiplies in these statements, and there are and 18 adds. If you count all the adds and subtracts, we'll count the subtracts as adds, so there's 18 of those across these. And how do you computed these 7 intermediate values, how do you get the actual answer out? Well, you do these little formulas, and you can go check the algebra and figure out that you actually, if you cancel everything out, you'll actually get what you want for m sub 1, 1, and so on. Okay? yeah, you do have to kind of stare at it a little bit to maybe work out the algebra to figure out. So what's the complexity of this algorithm? The cost of multiplying an n by n matrix using the Strassen algorithm is 7 times the cost of doing one that's half the size, half the dimension, plus 18, those are the 18 adds, operations that are on matrices that are have half the dimension, so n over 2 squared. And so it turns out that that turns into n times log base 2 of 7, or n to the 2.81. So this is asymptotically faster, meaning that if you have a large enough problem, it should be faster than an order n cubed algorithm. And it is in practice. The crossover point at which it becomes faster than a conventional matrix multiply algorithm depends on the machine. And here's a paper you can look at for references on it. Now, it turns out that what we talked about before is you don't care as much about the floating point operations you're doing. A few extras of those may not matter so much. What actually is really also important is that it reduces memory traffic. And so there's a reference here to a paper by Gray Ballard and others, and Jim Demble and others on showing that you actually improve asymptotically on the lower bound, the amount of communication that's required to do Strassen's algorithm. Okay, so this when Strassen had this algorithm, I think nothing happened for a little while. That was in the 65. And then there was a paper in 87 that said, wait, I can get it from 2.81 to 2.3, 7548. That was 1987. Whoops. And then some people, use my clicker here, I forgot I had one. And then actually this was a postdoc at Berkeley and Stanford that got it from 2.3758 to 2.37293, whatever it says there. That was a talk given here a few years ago. Then somebody reduced it. This is the 4th digit now. They got an improvement on. They can also extend the number of words, the memory traffic, and there's a thesis from 2015 on the data movement of these things. So we can't do any better than O of n squared, right? Because you got to read the matrices in order to compute something and write the matrices. So you can't do any better than that. So there's a paper, though, that says there's a possibility of something that is an O of 2 to the, n to the 2 plus epsilon. And then, you actually want to get the right answer if you're going to use these things. And it turns out you can you can make them numerically stable as well. And then you can, with these kinds of clever algorithms. And then you can, and this, by the way, this paper by Cohen, Umas, and Kleinberg it turns it into a group theory problem. So a bunch of cool math behind it. And it turns out that if you can do matrix multiply this way, if you want to do LU factorization or other dense linear algebra solvers and so on, you can use these ideas and also get the same kind of speed ups that you get from order n cubed to order n 2 to the whatever. N to the n squared plus epsilon is what I'm trying to say. So anyway, there's lots of interesting theoretical work here, and some of it does have practical values. It's not in terms of actually running faster. It turns out that these algorithms are not typically used in the libraries. One of the reasons is that the standard benchmark that we talked about, the LinPack benchmark, it says you have to use the order n cubed algorithm, because otherwise people are sort of cheating by doing less arithmetic. You're trying to measure whether the machines are faster, not whether your mathematicians are better. So, and many times the crossover point for what n has to be is so large that it doesn't really matter in practice. You don't typically multiply dense matrices that are that large. Okay. All right, so I've told you all about the things you can do to make these things go fast. Fortunately, the good news is that people put a lot of work into making these things fast inside of libraries. And those libraries, which you've already seen the word for, is BLAS. That stands for the Basic Linear Algebra Subroutines, the BLAS. And these are industry standards. They're actually, in fact, working even now on new variations, extensions of the standard. But it started actually in the 1970s, and what was in the BLAS in the 1970s, and that was the BLAS 1, was these vector operations. So things like dot products, so just summing together the product of a couple of matrices at what's called a Saxby or Daxby. So that's AX plus Y, and whether it's in single or double precision, you get an S or a D. And things like root sum squared, where you want it to sum together the square of a bunch of numbers and then take the square root. So there were a couple of reasons that people put these into a library. The main thing was in the 1970s, the most popular supercomputers were vector supercomputers. They had very long vector instructions, which I'll say more about, but I maybe gave you a little allusion to earlier. And so that made it, and the compilers, although the vectorizing Fortran compilers and so on were actually pretty good, they sometimes couldn't figure out when to use these kind of operations, and so they were a little bit too clever. So that was the original standard. Then in the mid-'80s, they said, well, let's try this for matrix vector operations, and so then you get operations like matrix vector multiply. Oh, and I should say that what's the computational intensity here? Well, the BLAS one doesn't help you very much in terms of improving memory performance. There are no tricks like tiling that you can do. Tiling is not a universally good idea. So if you're doing BLAS 1, there's not much you can do because you're just reading every element of the vector and doing a constant number of operations on it. It's actually computational intensity. If you go through the arithmetic here, we're doing you've got two vectors, for example, and you're reading one of them and you're writing one of them, and you're doing one flop. So your computational intensity on each location, your computational intensity may be 1. It varies a little bit depending on exactly what operation you're doing, but on order of magnitude, that's what you're going to get. And then BLAS 2, you might get a little bit better. You might get 2, but you're still not going to do very well because you've got the vector that you're reusing. So you get to reuse the vector, and you might want to tile it to make sure that that vector sits in the cache while you're multiplying the entire matrix through, if the matrix is really huge. But then we came up with the idea, or other people did, the idea of BLAS 3, and this is where we get to matrix-matrix operations, so matrix multiply and so on. And here, of course, you get to a ratio that's now much better, which is Q is F over M, and it can be up to as large as N in terms of the amount of reuse that you can get. So you can get those to go at a much higher performance than you can get for matrix vector multiply. We'll hear more about the rest of linear algebra later in the course. I just want to show you this graph, and this is, again, a really old machine. I'll show you a more recent machine in a minute, which is BLAS 1, BLAS 2, and BLAS 3 performance. And this is at the time, megaflops. So and this is the peak guaranteed not to exceed number, the dashed line there on the machine. And so the BLAS 3 number does get up pretty close to that. And one of the things we'll sometimes ask about is what is the problem size at which you get half of the peak performance? Because that'll tell us how steep this curve is. You want it to go up as quickly as possible. But the assumption, by the way, is that all the matrices start and end in slow memory, and that's why these things don't all sit up there, because you've got to spend some amount of time getting the data in and getting the data out. If you've only got a relatively small matrix, although you're running it as fast as you can, once you get the data into memory, it's not going to, you can't amortize all of that memory overhead. So this is looking at a number of different machines. This is BLAS 3 DGEM, as it's called. And matrix, and then matrix vector, DGEM-V. And so you can see across machines that you get quite a bit better performance, and this is a fixed problem size, I think, of about 500. So this is actually a more modern machine, although I couldn't actually find exactly what it was run on, but this was taken in 2013 by a group at ETH. And so there's the DGEM performance, and there's the DGEM-V performance. Now these are reversed, so what's going on? Well, we got to remember what we actually care about. This is running time in seconds. So yes, it's the case that DGEM runs at higher efficiency than DGEM-V, but DGEM-V is only doing order n squared flops, and DGEM is doing order n cubed flops. So DGEM-V is faster for a given problem size, but it's running less efficiently. So we take the same data. This is just to kind of remind you that we were looking at an efficiency graph, and there it is on the same kind of efficiency graph. There's DGEM running very close to the peak performance of the machine. This group did a lot of work on optimizing it, or the DGEM code, which is running much slower in terms of the number of gigaflops that it's running at. The y-axis here is gigaflops. Oh, actually, no, it's flops per cycle. They normalized it out. And what about the roofline plot that I talked about last time? Well, here's for a few different problem sizes. That's why you see some kind of squiggly looking lines here. This is DGEM-V sitting there under the bandwidth limited part of the roofline, and there's DGEM sitting underneath the flops limited part of the roofline. Okay. Questions? Okay. So just, these slides obviously are online, so you can go back and look at these references. There's a bunch of different papers you can look at for these. And I'll just mention that there are also a bunch of other slides that are online if you want to go and look at the lower bounds work, for example. We may talk about that more when we get to the linear algebra lecture, how you actually, more about proving various lower bounds on these algorithms, but I won't cover that there. I want to give at least a short overview of parallel machines, and we'll see how far we get in here. But it's going to be fairly high level, and I may have to finish a little bit of this next time. We're going to talk about just shared memory machines and kind of what it means to program on a shared memory model, and distributed memory machines and what that kind of programming looks like, and then vector machines. And I should say there is not necessarily a one-to-one correspondence between the machine and the programming model, but it is often the case that you're going to use, there's kind of a programming model that matches pretty well the hardware. Historically, we had a bunch of different architectures that came up in the 70s and 80s, and every time they had a new machine, they would have a new programming model that came with it. And then we got to the point where we were kind of all programming the same way. Unfortunately, I have to say, and I changed this from what was in the lecture last year, we're getting a little bit more into this machine-specific code again, because people are putting things like GPUs into their supercomputers. So we'll see a little bit more machine-specific code again. Okay, so what does our generic cartoon of a parallel machine look like? It's got a bunch of processors, and it's got a bunch of memories, and it's got some kind of an interconnection network that connects them all together. And exactly how they're connected together is going to determine how we might want to think about programming it, and also what things are fast and what things are slow on a particular computer. So the questions that come up is where's the memory physically located? So in many of our systems, we're going to have memory, some amount of memory that's sitting right next to a processor, but we could also put all the memory in one place and have all the processors just read and write to that memory. We could also, and then what is the connectivity of the network? Is there just like a grid, and every processor can only talk to its nearest neighbor, or even a line of processors? So you've got your little Ethernet cluster inside of your office, and you've got 4 machines, and you just cable them all together, kind of one in a row. That's going to give you a very different performance behavior than if they're all connected to each other. So when we talk about parallel programming models, here are some of the general questions you should ask. If somebody says, here's a new programming model, we really think you should try this one. First of all, the question is, how do I get parallelism? So what's the control model? How do we create parallelism? And what things are guaranteed to happen in a certain order? What things are possibly going to happen in parallel between different operations? There's a question of where does my data sit? Where do I put my data structures? Do I have data that's associated with some processor, some thread as we'll also call it, or do I have things that are shared? And so those are the two kind of questions that come up in terms of data. And then if I have only data that's private, if the only thing I have is each processor, each thread, if you will, has its own data, then you need to have some way of coordinating and communicating results. Otherwise, you can't solve any interesting problems. So then how will the data that you want to think of as being shared be communicated between the processors? We'll have various ways of synchronizing, so that's to make sure that processors don't get in the way of each other. And then what is the cost of all these things? So that's what really gives us the programming model. It's what's the mental model used for thinking about algorithms on your machine. So just to start with a simple example, let's assume that I've got an array A, and just a one-dimensional array A, and I want to apply some function to each one of the elements individually, and then I want to sum together the results of the application of that function. So the questions that come up is, where does A live? Is it all in one place? Did it get spread out somehow? What work is going to be done by each processor? And how are they going to coordinate to get a single answer out? Because if they're doing some different pieces of the work, somehow they need to get together to compute one answer. So here's a shared memory programming model for this. And the idea is, well, first of all, let me talk about what the shared memory programming model might look like. So generally, we're going to have a set of threads, which I've perhaps written here in a confusing notation as P, which stands for processor. So you can think of, for our purposes right now, a thread being the same as a processor. So there's going to be a thread of control that will run a particular piece of the program, and that's going to be running on one processor. And so I can, and in this shared memory model, though, what's typically the case is that I can dynamically create new threads. So I can pretend that I have more processors than I have by saying, pretend that I have 2n parallelism by saying, create 2n threads, even though physically I only have n threads. Each thread has a set of variables that are private to it. That's shown in the pink area down here. And each also has a set of shared variables that all of the threads can access. So here's a simple shared variable s, for example, the sum. You might want to put that in the shared space so that all of the processors, all the threads can read and write that shared variable. So they can all add, for example, to it and get the same result. And and you might put the array out there that everybody needs to read from, for example, in the shared part of the space. But you might have some variables, for example, loop variables and things like that. Your loop indices, each processor might have its own copy of that because they're working on a slightly different piece of the array at a different point in time. And the threads have to coordinate by synchronizing on the shared variables, and the point being that they can get in each other's way because they can both try to read and write the variable at the same time, and things can get rather confusing. So what do we do with our simple example running on a shared memory machine? Well, let's assume that our array A is much larger than the number of processors. Okay, so there's more than one element per processor. So what we'll do is we'll divide the array up, and we'll logically think of it as each one of the processors or each one of the threads will be responsible for doing the F application on some subset of A. Okay? So here we've got A, and it may be sitting in our shared memory, but we're going to say the first processor is going to be responsible for applying the F to the first 4 elements and then adding the result of that together. And then when each one of them has finished their piece, then they'll add all the results together and get that. So we have both data that's logically shared, that might be the array, and the global sum that comes out of the bottom, and things that are logically private, so that might be the 4 intermediate results that you're going to add together in order to get the sum. So this is some code that is not even quite pseudocode, and we'll go into a programming model called OpenMP later, but just to kind of give you an idea of conceptually how this looks is, let's say we just have 2 threads, and we just want to compute a sum. So we're done with the other stuff, and the processors have already computed their partial sums, and now they need to add them together. So now we just have something that says F is for each thread is going to add something to this shared variable sum. So that variable s is sitting out there in the shared space, and we're adding this together. Now the problem, which I guess I was supposed to ask you what the problem was, but anyway, the problem is that they can get in each other's way, and we call this a race condition. Okay, so the reason is that they're both trying to write s, and they're both trying to read s. So in order to understand why this is a problem, you need to go back to the lecture, for those of you who are for whom it's not obvious, to go back and think about, remember that I have registers in machine, and I only compute on things that are in my registers. And registers are never shared. Registers just live on one processor. And so, because those registers are sitting there right by where the little add and multiply units are. So what actually happens inside of this code is that each processor will, for example, read the value of s. So let's not even worry about this stuff on the right-hand side. We just want to, compute the update of s. We've computed the f of a stuff. And so what do they both do? So here's the bad thing that can happen is both processors at the same time, and they're not synchronized, so they can kind of run, one might run a little faster and one a little slower, but it might just so happen that they both read s at the same time. And let's say s is 40 at that point. And let's say that f of a1 is both 1, so you both want to add 1 to this thing. So the right answer is to get 42. But they both read 40. And they say, oh, well, I put that in my register. I add this other thing I've computed that was sitting in another register. I add that, which is a 1. And so they both add 1 to the 40, and they both write it back. And the hardware makes sure that if they're both writing at the same time, nothing bad happens, like the bits don't get interleaved or anything like that. So the reads and the writes will happen atomically. But they'll both write back 41, and you will have lost one of the updates. Okay, so that's a race condition, and so in shared memory code, we have to do something about that. We have to synchronize around it. And so there's a couple of different ways of doing this. Just see what happened to my. Oh, this is actually just, sorry, the animation for showing the race condition, so you can go through that if you want to, if you didn't like my verbal version. So what we're going to do instead is, in addition, or to add to this, to fix it, is we're going to put a lock in the code. So we have another variable, and it's called LK for lock. And it's a special kind of a variable that's a lock variable, and it has special operations on it. The operations you can do on a lock are lock and unlock, let's say. And so what you do is each thread goes, it adds up, gets its local result, and then it puts a lock before it goes and tries to do the add of the shared variable s. It will lock acquire the lock, and then do the add, and then do the unlock. So it'll do the read, and then the local add, and then the write, all while holding the lock. So you can think of this as a room that's got a lock on it, and inside that room is the variable s that you're trying to update. And so there may be two processors that are both trying to read it at the same time, but before they do that, the first thing they have to do is get a lock on the door. And when they get a lock on the door, they go inside the room, and they do all this work inside that region when they're holding the lock. And so only one of them can get in the room at the time, and so then you avoid the race condition problem. Any questions? Okay, so that's how that will work. Now you could say, well, why did I write it like this? Why didn't I just put this lock around the loop, for example, or around that statement that's inside the body of the loop? Any ideas about that? Yes?
Wouldn't that destroy any advantages you get from parallelism, because you have to keep accessing the same variable from each thread, or the same memory from each thread?
Right, so the answer is it'll destroy the advantages of parallelism, because in fact nothing will really happen in parallel. It's like you got two workers, and all the work that is to be done is sitting behind a locked door, and you'll say only one of them can get into the room at a time, and so one of them gets to do some work. Maybe one of them gets lucky again and happens to go back and get the same lock again and goes in and does another piece of work, and the other one kind of is sitting there with nothing to do, and so you don't get any real parallelism from it because of that. And in fact, it's actually worse than just kind of having just serial code. Just having one worker who doesn't have to worry about a lock, never has to acquire a lock, just goes in and does all the work themselves rather than coordinating with somebody else who is preventing them from doing anything at all. So you need to make sure that most of the work you're doing is not inside of what's called the critical region. That is where you're holding the lock. Okay, so that's just a little bit about shared memory. What does a shared memory machine model look like? Well, this is a cartoon of what a shared memory machine might look like. It's got a few processors in it. They've got caches, by the way. If you're not familiar with the little dollar sign, that's a little pun on cache. So each one has its own cache, and it's got some shared cache that can be down here, and some shared memory as well. And this thing, this interconnect, what I've called it here is a bus. And the way a bus works is kind of like that locked door. Only one of them can use the bus at a given point in time. And so hopefully, most of the time, the processors are working on things that are sitting in their cache, and therefore they get to make progress on them. And whenever they, and hopefully not too much memory traffic goes across here, because it's kind of like there's a separate little lock on this bus, just to anytime you want to go to shared memory or even to the level 3 cache, there's synchronization in there. And so this is actually a very convenient programming model because it's very close to the way you wrote your serial programs. A lot of times you can take a program and say, well, maybe I've just got this loop and I want some number of iterations to be done by each processor, but they still have the same variables. I'll just make sure that those variables are sitting in shared memory. I do have to be pretty careful about synchronizing them. If they're all going to write to the same variable, I've got to be careful about putting in locks and so on. But a lot of times my code doesn't change all that much. Yes?
Is there anything where they take advantage of addition being associative, where it doesn't necessarily matter what order you do it in? You can just put it in like a lock-free queue and then process?
Well, okay, so you said a couple of things there, but the question is, can they take advantage of the fact that plus is associative? And they can. And in fact, they were taking advantage of that even in the code that I showed back here, where they had a lock, because there's nothing that says what order they're going to get the locks. As I said, one of them can be lucky and get it twice in a row and get to do 2 adds, and then the other one can get it 3 times and do 3 of their adds. I mean, it just depends on things that are happening in the hardware, and all of that stuff that I talked about earlier that affect the performance of your serial code will affect the speed of these parallel processors, and also the overhead of trying to acquire a lock can cause them to, some of them can kind of starve and things like that. So yes, you are taking advantage of associativity here. We can also be more clever and put in hardware or some kind of mechanism that says, I know I want to do an add and I know it's associative, and so we'll call that data parallelism. And
yeah, because that still depends on the old value of S, but if you don't depend on the old value.
That's right. That's right. If you're all adding up your own local values, you could do your own local sum and then add that. Yes?
You typically pipeline so that each thread can have a different number of things that they have to add together, so that basically one will finish first and it'll add it to S, and then like the second thread will finish and then add it, just so that you're not like they're both done and trying to access us, but have to wait for each other?
Yeah, so the question was, do we try to sort of stagger it or pipeline it in such a way that we say the first processor gets, let's say there's, n over k, there's p processors, so n over p plus 4, the second one gets n over p plus 3, the third one n over p plus 2, so that they happen to get to the lock at different points in time because you gave them slightly different kinds of work. I have to say I don't know of that happening. People can disagree if you know of papers that are doing that. I think that usually it would be very hard to figure out sort of how much work would just make things line up perfectly. But yeah, that's it will come up when we actually talk about doing big reductions where we're adding a whole bunch of numbers together on a very large machine, and you want things to be a little bit unbalanced for that reason. Okay, so what's the problem with these shared memory machines? They seem kind of convenient, although you do have to worry about race conditions. But it turns out it's really hard to build a very large shared memory machine. And without going into a lot of details, this is the problem here. You've got this bus, and all the memory traffic is going over that. And so here's a performance study that shows, and this is the megaflop rate that you're getting as you're adding. You're running this is a real scientific application, and your running time is getting worse. And it's supposed to be a flat line that you're doing a constant amount of work as you add more processors. And that was running on a shared memory machine. And it has to do with contention for that bus. They're all trying to get access to the bus at the same time. So I'm afraid I won't be able to do message passing and distributed memory or data parallelism. So Aiden will cover that on Monday. But hopefully, and then he'll talk about a whole bunch of different application areas and how to think about parallelism in there. So thanks very much. Are there any final questions before they turn off the video? Yes, one.
Which processor should lock and unlock first, or is this something that's happening or hardware like on time?
Yeah, so in this shared memory programming model, there's nothing that says which one gets it first. What will happen in the implementation of locks is it will try to be fair in some implementations to make sure that if this processor got the lock last time, a different one will get it the next time around. Okay, thanks very much.